Good morning, everybody. I hope I have some good news for you today. Namely, today we're going to prove the second non-trivial and I believe quite interesting and powerful theorem of a semester. But before we do that, I still have to prove an elementary lemma, which I should have proven earlier, but you know how it is. This is not an encyclopedia, this lecture course. I'm trying to prove things on the go, which I needed. I'm trying to do the optimal things that I find in books, or I don't find in books. And this is why I have to make up for some missing material on the go. And this is a certain elementary lemma concerning invertibility in the path algebra. So yeah, but I first better take out my notes to make sure I don't screw up the notation and don't miss anything. Yeah, in the notes, this is lemma 2.7. Yeah, all that we need to assume is unitality. And the lemma is as follows. So let KE be a unital half algebra. Then an element in this path algebra, say X, is invertible only when X is equal to A plus B, where B is an element of the arrow ideal, such in KE bigger than 0, and A is an element of the commutative subalgebra of functions on the space of vertices. And, well, of course, that's not everything. And also A is invertible in this subalgebra. So A in the subalgebra is such that, this is our condition, there exists the inverse of this element in this commutative subalgebra. And when these conditions are satisfied, okay, so if X is invertible, then these conditions are satisfied. And we can write the inverse of X in the following way. Then X inverse equals A inverse plus D, where D is some element of the arrow ideal. Okay, so this is our lemma. You see, I didn't want to phrase this if and only if, because then I'd have to say something about D, and I don't care about D. All that I care about, you see, this is the whole point of this lemma, that if I want to invert an arbitrary element in the path algebra, that it means that I have to invert its part which is beyond the arrow ideal, and this inverse is in this part which is beyond the arrow ideal, in this commutative subalgebra, okay? So of course, because you have this direct sum decomposition of any path algebra into this commutative part, direct sum, the arrow ideal, you always have A plus B given uniquely, right? If you assume A to be in KE0 and B in the arrow ideal, then this decomposition here is unique. And if you assume that X is invertible, then in fact it implies that A itself is invertible, its inverse is in this commutative subalgebra, okay? And then the inverse of X can be written as A inverse plus D, where D is some element in the arrow ideal. This is a very elementary lemma. Let me prove it right away, and we will need it in the proof of our today's big theorem. Okay, so proof. So let X be A plus B and X inverse C plus D. So you see the X and X inverse define uniquely A and B, C and D, because I assume that A and C are in the commutative subalgebra. Oh, sorry, this should be 0. And B and D are in the arrow ideal. They are uniquely determined. Okay, then what happens? We can write 1 as X times X inverse. And when you calculate it, well, this will be obviously, you will have A plus B times C plus D. But because the arrow ideal is an ideal, then this X inverse belongs to the following set. It belongs to A times C plus the arrow ideal, because the 3 other terms must be in the arrow ideal. Right? But then when you look at this equality, this entails that A times, because 1 is of course beyond the arrow ideal, then you must have that A times C is equal to 1. Okay, so this is the conclusion we want to draw. So it implies that A times C is equal to 1. And now finally, to conclude with the proof of this elementary lemma, we note that this is the commutative part. So this is not just a one-sided inverse, a two-sided inverse. So as AC equals CA, C is the inverse of A. And by assumption, you see C was also in this commutative subalgebra. So this is an element in KE0. And of course, because we write down X inverse is by definition C plus D, we can write X inverse as just substituting A inverse for C. We can write X inverse as A inverse plus D. And this is exactly what was claimed, and this ends the proof. Okay. Any questions so far? I hope it is clear. I put it somewhere, more towards the beginning of the notes, because this is not directly related. I mean, this is related to the Jacobson radical story, but it is more general. It's useful in itself. Okay, so now I think we are ready to phrase the main theorem, which is about Jacobson radical, but to this end, let me recall the stuff. So remember that if R is a unital ring, then the Jacobson radical of this unital ring is one of the many ways to define it. We define it like this. This is a set, the set of all R in R, such that for all X in R, there exists, there exists the inverse of 1 minus, and how did I define XR in this ring? Okay, so this was our definition, and then it will be proven today, I hope, during the recitation class. So this is first thing I recall. The second thing I recall is the exercise that there exists in any unital ring, there exists the inverse of 1 minus, well, maybe I should write not x, but say Rs, if and only if there exists the inverse of 1 minus SR. Okay, this is a beautiful fact, which we're going to prove in the recitation class. But now with the help of this fact, one can prove that indeed the Jacobson radical is a two-sided ideal. Again, this is for the recitation class. Okay. But now we can actually prove something more. It follows from number 2 that you have well, this condition defining the Jacobson radical, right? Let me rewrite it. So I can claim that for all x in R, the element 1 minus xr is invertible if and only if for all xy in R, the element 1 minus xry is invertible. And this is very useful. This is an alternative definition of a Jacobson radical. Let me now show it to you why this holds. Oh, this is very simple indeed. Let x, y be arbitrary elements of our unital ring R. Now, since the radical, the Jacobson radical, is an ideal, it's not a completely obvious fact, but it's going to be proven. We can conclude that for any R in the radical, XR is also in the radical. Right? So by the definition of a radical, I know that there exists 1 minus y xr inverse in R, correct? Right? Because xr is in the radical. So by definition of the radical, for any y, 1 minus y times something in the radical is invertible. Okay? But now we use this property that 1 minus SR is invertible if and only if 1 minus RS is invertible to conclude what we want. So hence, by one of these properties discussed on the previous page, I can flip y over to the other side, and I can say that there exists the inverse of 1 xr y in the ring. So this proved not so easy to manipulate here. Okay, so this proved the interesting left to right, or if you want up to down implication. And the implication the other way around is trivial, because I can, this is a unital ring, I can take y equal to r. Okay, so let me just write it the opposite implication is obvious. Okay, so we have a missing lemma about the invertibility of elements in the path algebra using the arrow ideal. We have an alternative characterization of a Jacobson radical in terms of invertibility of 1 minus x r y. And I think that we are now good to go. Oh no, there's one more thing. Sorry, so there are a couple of more things that I need to talk about before I state and prove our main theorem of the day. So now we go to algebras, and remember, as Anya was explaining, there is a slight difference between ideals in the ring and ideals in the algebra. Namely, every ideal in a ring is an ideal in every ideal in an algebra is an ideal in the ring of which is the image of a forgetful functor applied to this algebra, right? So if I forget vector space structure on an algebra, then any ideal of this algebra is an ideal of a ring. But we have this additional condition that this is not just a ring ideal; it's also a vector subspace. Okay, so we proved in the ring theoretic setting that the Jacobson radical is an ideal of the ring. So now we have to prove that if it is an ideal in an algebra, if this is a ring ideal in an algebra, that this is actually also a vector subspace, and then we can claim that this is an ideal of an algebra. Okay, so this is an elementary argument, but let me do it. On the next page, of course. So now we go into algebra. So next, if A is a unital algebra over a field K, then the Jacobson radical of A, sorry, I wrote R, is an ideal of A. And to see this, it suffices to show that this radical is a vector space. Well, no, it's closed under the addition, so all that we have to check is the scalar multiplication. Okay, but this is very elementary. But still, let me write it down. I claim that for any element lambda in the field K and X in the ring R, we have that there exists the inverse of 1 minus XR. Well, actually, I want to write it like this. Lambda XR is invertible. Of course, if and only if, this is an obvious tautology, 1 minus X and now times lambda R is invertible. Okay, so R, well, maybe I should write here R in the Jacobson radical of A. Okay, so by definition, if R is in the Jacobson radical of A, then 1 minus anything times R is invertible. I write this anything as lambda times X, where lambda is an arbitrary number and X is an arbitrary element of my ring. And I just trivially shift lambda to multiply R instead of X. I shift the parentheses. And now I say, hey, look, I have lambda R, and for every X in the ring, 1 minus X times lambda R is invertible. But this is by definition, it means that lambda r is in the Jacobson radical. Okay, so lambda r is in the Jacobson radical of A, as claimed. Okay. And we can also quickly check, this is another fact which I need about the Jacobson radical, that if I is a nilpotent ideal of A, then it is contained in the Jacobson radical of A. So one might think that the Jacobson radical of A is like the maximal nilpotent ideal of the algebra. And I think we were checking it with Anya that she was checking that under some assumptions, in fact, this is true, but it's not true in general. Okay, I don't remember, so something about Archimedean rings, right, Anya? Do I remember correctly?
Yes.
Okay, but we want to work in full generality. So all that I don't want to make any assumptions about A, just that it's a commutative. Sorry, no, not commutative. Only that this is a unital algebra over a field K, and then any nilpotent ideal of this algebra must be contained in the radical. And well, this is an elementary thing to check. So to see it to this end, note that if I have that I to the power n plus 1 is equal to 0, remember that's just the definition of being nilpotent. There exists an n, natural number n, such that I to the power n plus 1 is equal to 0. If this is the case, then for any r in this ideal, you can explicitly write the inverse of 1 minus 1x. This is 1 plus x squared dot up to xn. Okay, this is obvious because if I multiply it by 1, well, I just have the sum from 1 to xn. If I multiply it by x, then I have a sum from x to xn plus 1, except that xn plus 1 is 0. So in fact, I have just the sum from x to xn. This is with the opposite sign, so everything will cancel except for 1. And this proves that the inverse of 1 minus x is exactly that sum. Okay. So we can immediately conclude. Why did I write x? Sorry. This is, I was, no, oh, it's correct in the notes. I screwed it up here. I'm so sorry. Of course, this is r. You should have yelled at me. It's like it's like one of his jokes. Let x be a space, call it y. Let r be an element of an ideal, write it as x. No, sorry. This is what I meant. But now we can conclude that if we take an arbitrary x in the algebra, and of course, we still have an arbitrary element in this ideal R, in the ideal I, then there exists the inverse of 1 minus XR. Right, this is because the I is by assumption an ideal. It's a nilpotent ideal. So for any x in A, x times R, and R in I, x times R is in I. and then we have an explicit inverse. So if you want to have an inverse of 1 minus xr, you just substitute xr for r in this formula, and this is your inverse. Okay, so if you have any element which is an important ideal, it satisfies the condition of being in the Jacobson radical. So this proves this inclusion. Okay, and it's completely general. All that I assume about my algebras is that they are uniform, because otherwise the concept of the Jacobson radical is more complicated, and I don't know to go into this. Okay, it seems like we are done with the preliminary work, and I can finally state the theorem of the day, which actually is a very short theorem to state. Ah, my handwriting is pathetic. So let KE be a unital path algebra. Then its Jacobson radical is something very explicit. It is the linear span of the following elements. So I take my canonical elements of my canonical basis, pi p, and all I have to tell you is what are the paths p. So p is a path, of course, which is not a vertex and not a subpath of a loop. Okay, this is our theorem. And let me say why it is exciting. Well, it is exciting because it's completely general. I mean, almost. The only thing we assume is unitality. And when you look into books, everywhere you find a much, much simpler version of this theorem, which assumes your graph to be finite and acyclic, or at least acyclic. You see, when your graph is acyclic, then it's obvious that this set defined on the right is simply the arrow ideal, okay? Because basically the condition that of not being a subpath of a loop is vacuous because there are no loops. So the only thing you are discarding are vertices. So say you take the linear span of xp's where p is not the vertex. That's exactly the arrow ideal, okay? So for acyclic graphs, you have the obvious answer. This is just the arrow ideal. And well, then you can prove, and it's much easier, that indeed the Jacobson radical of the path algebra of an acyclic graph with finitely many vertices is exactly the arrow ideal. This is what you find in books. And then you have the warning that if you take a graph like this, just consisting of one loop, then the Jacobson radical is 0. So you should not think that it is always the case that for any graph, even for a non-acyclic graph, the Jacobson radical is the arrow ideal. Well, of course it is not, but you can explicitly say what it is. And even though we tried quite hard to find it in the literature, we couldn't. So we are in a funny situation. We prove a theorem much stronger than what we can find in the literature. But on the other hand, I just don't believe that nobody proved it like 50 years ago. So if anybody could find from me a reference for this theorem, I will be eternally grateful. We tried and we failed. I don't know where it is done, but I don't believe it is not done, because it's like the very obvious question. The Jacobson radical is used all around path algebras. So everybody must have asked himself or herself the question, what is the Jacobson radical of the path algebra, at least of the unital one, okay? But okay, we give an answer. So we will do the proof. This will take quite a long time. It's 10 o'clock. I hope I will make it within 1 hour. Are there any questions concerning the formulation of a proof? I hope it's clear. So for starters, let us remove the case of E being the empty graph. So the theorem is trivially true oh my goodness. For E being the empty graph, right? Because when Ke is just the zero algebra, and well, this is an assumption that the span of an empty set is zero, so the Jacobson radical is zero, and of course this is obviously true if you look into the definition, because we have just put zeros everywhere, okay, and zero inverse is zero in the zero algebra. So this is trivially true. There is nothing to say. So we assume, for the sake of a peace of mind, without the loss of generality, so WLOG, that E is not empty. Okay, and at a certain moment it will be useful. Whenever I take, oh, let's take the canonical basis. Well, if we have the empty graph and there is no canonical basis. So this is just to avoid some silly discrepancies like this. Okay, and now let me introduce, you see, that set is kind of funny. I don't want to write all the time, P is not the vertex and not the subpath of a loop. So let me introduce some notation. I want to denote the set of such paths as J. Okay, and then we will be able to have a more succinct notation. So next, define J. Exactly as the set of all paths. Of course, when I say paths, I mean finite directed paths. All paths such that P is not a vertex and not a subpath of a loop. Okay. So now it will be easier to write certain things. It's, as you can guess, it will be all over the place, this set, as the theorem is basically about this set. Okay. Now, remembering that all nilpotent ideals, nilpotent is one L, as all nilpotent ideals are contained in the Jacobson radical of Ke. To show the inclusion span of chi P with P running J, you see now it's much simpler to write. To show that this is included in the Jacobson radical of Ke, it suffices to prove the following lemma. Well, basically that this thing on the left-hand side is a nilpotent ideal. In fact, there will be a little bit more in this lemma, but I want to have it in one place. Okay, So again, let K be a unital algebra, a unital path algebra, and let J be the set of all paths P that such that P is not the vertex and not the subpath of a loop. I'm not going to write it. That's the same preamble as before. So what we claim is that when it comes to paths, if I take all paths in E that are not in J, but in some sense, this is a multiplicative set. So when I square this set, this is contained in the set itself. So in other words, you should read it like this. If you can compose two paths that are not in J, I mean, they might be not composable, but if they are composable, and if you compose them, then you'll again get a path which is beyond J. Okay, so this is what this inclusion means. And we also have another inclusion. Oops, I didn't mean this line. And the other inclusion is the following. If you, so let me write and. If you take a path in J and compose it with any path, or if you take a path, any path in P, in E, and you compose it with a path in J, then this will give you a path in J. Okay? So this is first thing that we claim. And this is what I promised you in my email. Okay, I said that in the recitation class, we're going to prove some important properties of a certain set. So these are these two properties that I mean. And I'm going to show it in the recitation class. And then I don't remember who has this problem 7.3, but then somebody is supposed to prove that this span of chi-p's with P and J is actually a two-sided ideal. A nilpotent ideal, sorry. Yeah, so that is a nilpotent ideal. So first that is an ideal, and then that is nilpotent. So somebody has to prove it in the recitation class. And okay, great. So we will do it. So I'm not going to prove this lemma right now. We are going to do in recitation class. So, but let me finish writing it. Furthermore, span of all these chi-p's with P running J is a nilpotent ideal. Okay, and now it's clear what I meant. If you remember that all nilpotent ideals are in the Jacobson radical, if we prove that the span of XP's with P running over J is a nilpotent ideal, then of course it must be in the Jacobson radical. This is what we argued for before. So this lemma we're going to prove later on. And in fact, this lemma, although not trivial, is actually much simpler than the rest of the proof. So this one-way inclusion that this span is in the Jacobson radical is actually much easier than proving the other way around inclusion. And this is what I'm going to do. I hope 51 minutes is enough. Okay, so to prove the opposite inclusion, you take an arbitrary R path algebra KE and use the canonical basis So you see, if it were the empty set, I wouldn't be able to call it the canonical basis. And use the canonical basis to write it in the following way. To write R in the following way. So this is why I have this column on the right hand side of the quality sign, because by having this stuff on the right equal to R, I define coefficients that I write in this finite linear combinations. I define them unique because this is a basis. Okay, so first I'm taking paths that are in J, but I'm choosing some finite subset of J. Okay, and I have alpha P, chi P. Now I'm taking vertices. Okay, so I'm summing over some F2, which is in the set of vertices. Well, here it's obvious that F2 is finite because E0 is finite. And I write alpha V, chi V. And finally, I take the sum over everything else. Say Q in F3, which is now a subset of FPE less J union E0. Okay. So all these sets are disjoint. J, E0, and FPE less J and less E0. And they also give you the whole set of all paths. So it is clear that I can always write R as a finite linear combination of that form. Just let me finish the formula. Just here alpha Q, chi Q, right? The only thing that I'm doing is I'm splitting this set, labeling my basis elements into 3 disjoint parts. And I'm using that this is a basis. That's all. Right? But I want to be a bit more precise with these Fs, where F1, F2, and F3 are finite sets such that all coefficients labeled by them are non-zero. Right, because if some of these coefficients are 0, why bother? We can just keep it from the sum. So we can just assume that we have these finite subsets F1, F2, and F3, each of them belonging into a different disjoint part of FPE. And we take only such elements in these 3 subsets, so that the coefficients that I need to use in my finite linear combination presenting R are non-zero. Okay. And now what we assume that for any x, y in KE, I have 1 minus x minus R times y is invertible. So in other words, I assume now that R is in the Jacobson radical of KE. And I want to prove that in fact it's in this nilpotent ideal. And the way to prove it is to show that the sets F2 and F3 are necessarily zero, necessarily empty. If I prove that this assumption that for all xy in KE, 1 minus x r y is invertible, if this implies that the sets F2 and F3 are empty, then I'm done. Because it means that then R is in this linear span, of chi p's. P should be a subscript, not a superscript. this is exactly an element in our ideal that we want to prove. So this will give us the other way around inclusion. Let me write it. Our goal is to show that F2 is empty and F3 is empty. But it's a long way. It's a long way. It's not so immediate. So first, I'm going to prove that F2 is empty. Of course, by contradiction. First, suppose that F2 is not empty, and take some vertex u in F2. Okay, if it's an empty, then it must have at least one element. Now we obtain the following. You see, x and y is arbitrary, so I can in particular take x and y equal to chi-u, and I can compute it to be x chi-u times r times chi-u. This will be equal, here I have the sum over P running some other set F4, which is a subset of J. I still have alpha P chi P. And here I'll have alpha U chi U. And one more term. I have sum over some F5 now, which is again a subset. Well, this is now a subset of F3. And here I have alpha Q IQ. All right, I hope it's clear. Let me go back to the previous slide so that you remember what we are computing. You see, here's my expression for R. And I put chi-u from both sides. I sandwich R between two chi-u's. So of course, for starters, coefficient will not change because all that will happen, I'll have these chi's multiply with each other and coefficients will remain the same. Okay, however, some things will be cut out because if P is not a loop which starts and begins at U, then the sandwiching will kill it. And the sum will be over, if you want, the subset of F1, which counts loops based at U. Now with vertices is obvious. Remember that these are orthogonal idempotents. So out of the sum, the only thing that can survive is alpha U chi U. And you know that it survives because remember, by assumption, F2 is non-empty and it contains U, okay? So we have a non-zero coefficient alpha U times chi U in the sum. And this will be the only guy that will survive the sandwiching between chi U's because chi U's will kill all other idempotents. And then finally, we look at the last terms. Again, basically what happens that out of the set F3, we'll select loops that are based at U, all right? So this subset, whatever it was, F5 is the subset of F3 consisting of all loops based at U. Okay, so this is the formula, but let me also write it, what I just said, where F4 and F5, again, finite sets, they are subsets of finite sets. They have not lost finiteness. And moreover, if I look at the 5, these are just loops. of all elements of F5 are loops based at U. Okay. Now, since 1 minus alpha U inverse chi U R belongs to, you see, I look at this chi U R chi U, I divide it by alpha U, which is not 0, and look what happens. These elements in the first sum are in the arrow ideal. The elements in the third sum are in the arrow ideal. Remember, vertices are removed. So F3 is the subset of paths where you remove J and remove vertices. Okay, so these sums at the left and at the right are in the arrow ideal. And the only thing which is not in the arrow ideal is alpha U chi U. So when I have, but now I divide it by alpha U, so I have only chi U left. So 1 is also the only part, is also beyond the arrow ideal. So the part which is beyond the arrow ideal is 1 minus chi U. So this is the sum of all elements. And remember that 1 is the sum of chi V, where V runs all vertices. And if I have 1 minus chi U, what it means that I have the sum, but now not over all vertices, but over all vertices but U. All right. So now and all the rest is in the arrow ideal. Again, I have this spurious line. So I can write it as an element of the following set. I have a sum over all V less than U. Sorry, not different, not equal to U of chi V plus the arrow ideal. Okay. But now remember the lemma I proved at the beginning. Let me call it by the lemma. And scroll back. By this lemma, okay? I have a unital path algebra KE, and I have an element of a form A in the commutative subalgebra plus B in the arrow ideal. Then if it is invertible, it must be of the form A inverse plus D, where A is this part beyond the arrow ideal. And you see that it immediately leads to a contradiction, because the sum of all but one projections cannot be invertible. Okay, now since we have this for the inclusion, we have this property that 1 minus alpha U inverse chi U R chi U is in the set which is of the form the sum of all but one projections, vertex projections, plus the arrow ideal. And by the lemma, we can conclude that the sum over V not equal to U of chi V is invertible. And this gives a desired contradiction because the sum is a function on E0 vanishing at U. And you know that if you have a function algebra, and this commutative subalgebra of the path algebra is a function algebra, as we discussed at length, then the only invertible functions are functions that are nowhere vanishing. But it vanishes at U, so it is not invertible. Okay? So now we can conclude that F2 is empty. So now I can write my R as the sum over P in F1, which is a subset of J, chi P, alpha P chi P. Then I skip this part with vertices because F2 is empty. Remember the convention that summing over the empty set means writing 0. And I have only the other sum, well, which is as before. So it's Q. No, this time it's Q. And Q runs F3, which is a subset in FPE, that's J union vertices. Okay. Alpha Q chi Q. So I have one term left, one term less. Okay. So now we will try to prove that F3 is also empty. Any questions so far? Okay, half an hour left. Hope we can make it. So suppose now, I think this is the most difficult part of the proof. Suppose now that F3 is not empty. And take an element in F3. But remember, this is a path which is a subpath of a loop. So then there exists a path B such that AB is a loop. And now let me make it clear. If you think about it long enough, it becomes obvious. But let me clarify it on another page. Okay, so first, I never told you that this loop is finite. Okay, but if you have an infinite loop, then because it's a loop, it means that starting from some sufficiently small number, sorry, this is -1 minus n. The starting point of E minus n will be the same. I mean, the starting point of any edge which is to the left from E minus n will be exactly the same as the starting point of E minus n, and the same about the end point of EM. The end of any edge which is to the right of EM will be the same as the end of EM. This is the condition of having a loop. It might go to infinity, but from a certain moment, you will have the stabilization of the endpoints. So you'll be able only to adjoin loops and edges with the loops. And now this means that if I have something which is part of a loop, it's actually always part of the finite loop. All right. So I can take my A and I can write some E minus n, blah, 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 up to E minus 1, and then I can write E1, sorry, dot, 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 up to EM, and it is a loop. So it means that the end of EM is the same as the beginning of E minus n. right? But then because of a compatibility condition, of course, I can put it in here, right? So I can now write A, E1, EM. And remember, the end of EM is the beginning of EN. So I can write E minus N, dot, 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 up to E minus 1. And guess what? Because this is a path, then the end of E minus 1 is the same as the beginning of A. So it is a loop. That's why without any loss of generality, I can say that there exists a B such that AB is a loop. Okay? That's something you're supposed to do in your mind. I'm not typing it in the notes. But you have to bear it in mind that, that without the loss of generality, I know that there exists a B such that AB is a loop. Of course, it would be the same as saying there exists a C such that CA is a loop. We can choose any side, right or left. I chose right. Okay. So let me skip it. I trust this is obvious, that then AB is a loop. And we continue our argument. We write the following element. One minus chi SA. So I take the starting vertex of our path A, R, and I take chi of B. So now I chose as my X chi SA, and I chose as my B chi, as my Y chi B. All right, that's something that must be invertible. But first, let me compute what it is. Well, or maybe it's to say compute is to be a word, but I can just write it more explicitly. You just have to remember what happens, what R is right now. You see, this is our R, and now we are sandwiching it. On the left we have chi SA, and on the right we have chi B. Okay, but remember that SA is the same as the end of B. So what happens here is that everything that remains, well, will be loops. So for starters, because I multiply on the left by KSA, I'm killing all paths that don't start at SA. Okay, so now I'm looking at all these paths, P and Q, that actually start at the vertex S of A. But now I'm multiplying on the right by KB. So if this B composes with P and Q, if it doesn't compose with P and Q, fine, it dies, it's 0. But if it does compose with P or Q, then I have PB or I have QB. And I already know that P starts at SA. But remember, AB is a loop. So the end of B is the beginning of SA. So this means that the end of PB and the end of QB is the end of B, but the end of B is the beginning of A. So this means that only loops survive. I mean, when I have a sum and have this multiplication. So this is what I will attempt to write right now. So now I have some other sets. And of course, coefficients are unchanged. When I multiply by chi's, coefficients are unchanged. So I still write alphas, but now the sets over which I sum will be different. So I have F6 right now, which is in J. And then I have F7, well, which is of course a subset of F3. Oops, I forgot to write here. Alpha P chi P minus alpha Q chi Q. And now, in fact, yeah, I'm not so happy with my notation. Yeah, but you see, P and Q are dummy indices. Okay, you should think about P and Q as PB and QB are actually SAP B and SAQB from the other sum. Okay, these are just dummy indices, and so I can still denote them by P and Q. It's just that I have to specify what these sets are, F6 and F7, right? And this is what I'm going to do right now. Okay, guys, half a page left to the end of the proof. Not bad. So of course, we are finite set. Maybe I'll not write it, it's obviously they are finite. And AB belongs to F7, so this is not an empty set. Remember, we assumed that A is in F3. So even, oops, yeah, thank you. So even if everybody else dies, there will be one thing in that sum over F3 that will not die, namely alpha A, chi A. This will not die because when I multiply it by chi B, I'll simply get alpha A, chi AB. Okay, so this loop will be in F7. This is non-empty, therefore. Maybe everything else dies. Maybe you have many more elements, but I definitely have AB as an element of F7. Yeah, and all elements of F7 are loops based at U. I sort of don't care about this sum over F6. It's all of this is in my nilpotent ideal, which is the span of chi p's with P running over J. This is an element of this nilpotent ideal. And that's something I don't want to kill. Whatever it is, I don't care if it's 0 or non-zero. 0 is still in the ideal. What I care about is this third part of my expression, the sum over F7, okay? So here I note that this is a non-empty set because it contains A times B, or A composed B, and it consists only of loops because all other elements of F3 died as the result of sandwiching by chi SA from the left and chi B from the right. Okay. And now we know that this is invertible, okay? So I use again the lemma from the beginning of the lecture. The inverse of this element must be of the form. Well, look at this expression. This sum over F6 is, of course, in the arrow ideal because my nilpotent ideal is in the arrow ideal. And then here F3 is the set of paths that are not in J and that are not vertices. So again, vertices are excluded, so I'm in the arrow ideal. So these two sums are in the arrow ideal, okay? So I have 1 plus something in the arrow ideal. So therefore, I know that the inverse of such an element must be the inverse of 1, which of course is 1 plus something in the arrow ideal. And I can write it down in the following way. I can write it as, now I'll introduce primes because now this is really a different animal, okay? I take P prime running some set F8, which is a subset of J. And now I have B P prime, chi P prime. So these are no longer coefficients alpha. This is why I changed them to beta. And sorry, this is not P1, but P prime. P prime, P prime. And now I have to take the other part of the sum. So now I take Q primes running F9, which is now a subset of FPE less J union vertices. Okay, so here I have a part which is spanned by vertices. Here I have part which is spanned by J, and here I have all the rest. So things that are spanned by elements that are neither in J nor in the set of vertices. Handwriting is really pathetic. Okay. And I have beta Q prime I Q prime. Okay, this is already something. I mean, we know that the inverse of a form 1 plus something. This will help us in our calculations. And again, by definition, the sets F8 and F9. Sorry, why do I write 9 as G? Are finite sets such that all coefficients labeled by them are non-zero. Okay. So now what I'm going to do, I'm going to multiply, you see, 1 minus chi SA R chi B. I'm going to multiply it by its inverse. And I can do it in two ways, of course. I can take first 1 minus blah, blah, blah times its inverse, or I can take first the inverse and then 1 minus blah, blah, blah. In both cases, oops, I do. So this is really very strange. I mean, I'm wired. This is not Wi-Fi. I'm connected to high-speed internet over the cable, and in both computers, everything vanished. This is so weird. I cannot even blame my laptop because it happened on both computers. So now what? If I go to share screen, will it? Yeah, and all my writing is gone. Wonderful. Oh no. Zoom sucks. Now we have a proof of it. Now, if it happened at home, I would blame my internet connection, but it happened over the wire here at IMPAN. So this must be the instability of the Zoom application. Okay, can you hear me, guys? Can somebody say something?
Yes.
Yes, I can hear.
Good, thanks.
Yes.
So I'm really sorry about this. All of a sudden, on both computers, Zoom vanished. Boom, vanished. Nothing. It's gone. And well, this is bad news because I cannot now go back to what I wrote. I have to write it again. And I don't believe it was the internet. It was something strange with Zoom. The internet here over the cable is perfectly stable. Okay, anyway, remember that we were multiplying two terms, two things in two orders, which should give us 9 terms, and we make it equal to 1. And one of these terms is equal to 1, so the 1 cancels on both sides. So I have 8 terms equal to 0. All right. So this is what I do now. I multiply 1 minus chi SA R chi B by its inverse. And I know that this is equal to 1. So in other words, I know that if I just subtract 1, then this is equal to 0. Okay, so basically what I'm going to do, well, in this form here I have 4 terms. One of them is 1. So basically I have that the remaining 3 terms sum to 0. Okay, but now when I write this down, I mean this sandwich as 2 elements, then in fact these 3 terms will be 8 terms. So 8 terms after plugging in the appropriate formulas that so gracefully vanished. But now let's look at these terms. And now remember this property that if I look at my set J, then anything and any path composed with a path in J, and any path in J composed with any other path, this gives me a path in J. Either they don't compose or they give me a path in J. J, not. This would be a true statement, but trivial. So this is what we remember. And because you see, when you look at these 8 terms, yeah, maybe I should. Okay, maybe let's finish maybe writing these things from the lemma. Okay, and the other property that we claimed in the lemma was that if I take stuff away from FPE that is in J, in fact, I can take away even more. I can also remove vertices. And if I square it, I will again be in this set FPE. That's J. Okay, the lemma actually makes a statement only FPE minus J. All right, but you see, this is not the problem, because on the right hand side, if you would like to get a vertex, it would come only out of multiplication of vertices. So if out of the set FPE less J, I also remove vertices, then when I square this set, obviously there is no way I can get vertices. Okay. So that's why this is true by the lemma. Yeah, I hope it is clear. So it is obvious by the lemma that this is contained in FPE minus J, and I claim that I can skip vertices because there is no way I can get a vertex by concatenating paths that are not vertices. And this is what I would have to do here if I remove vertices. So by the lemma, this is true. And now how do we use it in multiplying things out? So remember that this 1 minus chi SA r chi b, that's something that we wrote the following way. One minus chi SA r chi b. This is 1 minus sum over p in F6. And this is the J part, alpha p chi p. Well, this is a bit of a nightmare if my writing keeps on disappearing. It's now the second time Zoom disappeared. And the internet is stable all the time. It's not the question of internet. So frustrating. Well, I just have to count on your memory. I'm sorry, I cannot rewrite it all the time. This way I'll never finish. No. Okay, I will just rewrite these two things because I really need it. So that you see what I'm doing. 1 minus chi SA r chi b is 1 minus sum over p in 6, which is in J, p chi p. I take Q's running F7 over the rest, alpha Q, Q. And I have this stuff inverse, which I write as one plus sum over P prime running F8, and this is my part in J, and plus sum over Q prime in F9, and that's my part beyond J and beyond vertices, okay? So here I have a beta P prime chi Q P prime, and here I have a beta Q prime chi Q prime. Okay, so I multiply these things out. I have 9 terms. This is equal to 1. So 1 cancels on both sides, and I have 8 terms that are equal to 0. But now I want to see how these 8 terms are obtained. So 5 out of these 8 terms will belong to J by the property which so gracefully vanished, right? Because remember that if I compose a path in J with anything on the left or right, it will be a path in J. So if I take the second term in the first equation on the right-hand side and multiply by everything else, then all these 3 terms will again be spanned by paths that are in J. Okay, the same goes true for the second term on the right-hand side of the second equality. But I cannot count anymore the term which is the sum over f6 times the sum over f8. This is the same sum. So now I'll get only 2 more terms. But altogether, I'll have 5 terms that will somehow be sums over elements in J. And now I look what happens with the remaining, and I don't care about them. This is from another part. Remember that all elements are linearly independent, and if I have disjoint subsets of my of FPE, then elements labeled by the subsets are in different direct summands of my algebra. Okay, so they vanish separately. So now I'm only interested in what goes outside of J, and this can be only out of these 3 other elements. So what can happen? Well, I have sum over f7 times 1. I have sum over f9 times 1, and I have sum over f7 times sum over f9. So these are my 3 terms when I get elements which are labeled by paths that are beyond J and beyond vertices. And I know that this is, of course, there is no problem with f7, no problem with f9, because that's by assumption. But I also have to note that f7 times f9 is again beyond J and beyond E0. And I know it by this property, this multiplicative property that I stated before, okay? And by the linear independence of the basis elements, of any finite subset of the basis, in fact, to be more precise, I can claim that the sum of these 3 terms must vanish separately. Okay, the basic idea is the following. So once cancelled out, I have an equality in the arrow ideal, and out of these 8 terms, I have 5 which are in one direct summand. They are simply in this nilpotent ideal I'm interested in, and I have 3 terms which are outside of this nilpotent ideal. Yeah, they are in the direct summand, which is outside of an important idea. So if I have that things, if I have A plus B equals 0 and A is in one direct summand and B is in the other direct summand, then both A and B must be equal to 0. So I can conclude now that these 3 terms add up to 0. So let's see what these 3 terms are. So I have sum over Q prime in F9, beta Q prime chi Q prime. Then I have a minus sum over F7, sorry. And I have here alpha Q chi Q. And I also have to subtract. Well, now depends in which we multiplied things. It's not really important. Let's say that we multiplied 1 minus blah, blah, blah times its inverse, okay? So this will be the sum over Q in F7 and Q prime in F9. And I'll have here alpha Q beta Q prime, and here chi Q prime, okay? And this must vanish. Any questions here? We are almost done. Well, it's 11, but I will need a few more minutes to finish. We must finish it, but we are almost done. Okay, so it all boils down to this equality. And we still have some cases. I think I'll finish within 15 minutes. Okay, and all of this is due to so let me write, hence this equality is true due to the linear independence of any non-empty finite subset. both the canonical bases. Yeah, because we have sums over canonical basis elements. So if we sum over disjoint subsets, labeling elements of a canonical basis, they are of course in different direct summands. And I use this linear dependence to claim that things must vanish separately. Therefore, I have just that the summing up of these three terms must be zero. Okay. So now let's make the following. We have to consider two cases. I have to consider two cases. If F9, see, Anya, this is where the proof that we discussed gets more complicated. That's what we sort of skipped on Wednesday. So if F9 contains no loops, based at S of A. Remember, we argued at length that if I look at the other sum, well, I'm just talking about loops based at S of A, at least in this part, which is beyond J and D0. So now let's see what happens if we assume that F9 contains no loop based at SA. But then we get a contradiction. With F7 being non-empty. And now I wonder why this is true. Let's look at the formula. Right. Okay. Right. You see, if there are no loops in F9, then no Q prime is a loop, and no QQ prime is a loop. When you look at this sum here, well, this will be either 0 or chi QQ prime. If Q prime is not a loop, then QQ prime is also not a loop. Okay. But this means that out of these three sums, you have loops only here in the sum over F7. But then this means that the sum over F7 must vanish separately, which means that all these coefficients must be 0 by the linear dependence, which basically means by the definition of a set F7 that it's an empty set. So this is why I have a contradiction, okay? So now we can assume that there is at least one loop based at SA in F9. So if there is a loop based at SA in F9, then, as it is a finite set, there exists a longest loop based at SA and from F7, sorry, F9. Okay. If I have a non-empty finite set, then it meets the maximum. Of course, here is the maximum by the length, right? And it's A because you might have many different loops of the same length, but there exists a longest one. But now also, S F7 is a non-empty finite set, but now please remember of loops. Based at SA. There is a longest such a loop. Okay. And now let's call these loops somehow. There exists a longest loop D based at SA from F9. There is a longest such a loop C. Okay. So this is a loop based at SA from F7. Okay. But hence, CD, of course, loops based at the same point compose. CD is a loop. Remember, a loop is of length at least 1. So this is a loop based SA that is strictly longer than any loop in F7 union F9. Right, if I multiply a longest loop in F7 with the longest loop in F9, of course, I get something which is longer than any loop in F7 and any loop in F9, remembering that the length of a loop is at least 1, okay? But now, why is it a problem? Well, combining it with the obvious fact that CD is equal to C prime D prime if and only if C is equal to C prime and D is equal to D prime. We conclude the desired contradiction. Why? Well, you just have to go back to this formula. So this is really, really a key formula, okay? So here I have my loop CD, right? In the sum over F7 and F9. My loop CD lives in here, okay? And it cannot be cancelled out by any element of a sum over F7 or F9 because any loop in the other sums is shorter, strictly shorter, right? So there will be no cancellation coming from the first two terms. But then you might think, well, but maybe this coefficient times chi of my longest loop CD will cancel by some other one, right? When you have natural numbers, I mean, you can write 5 by 5 plus 3 as 4 plus 4. So the fact that 5 plus 3 equals 4 plus 4 does not imply that 5 equals 4 and 3 equals 4, okay? But with paths, we have it. If I have that concatenation of two paths is equal to the other concatenation of two paths, or maybe this is, wait a second. Now I realize that this is actually not true. This is true if they are if they are the same length. Okay. Yeah. So this is more subtle. I have to write down. Sorry, this is it's tiny bit too fast. For C of the same length as C prime and D of the same length as D prime. Okay, so I'm looking at my longest loop CD in the set F7 union F9, and there must be another loop which is also a longest loop, but the only way to get such a longest loop would be by having another longest loop of F7 concatenated with another longest loop of F9. So of course, what I wrote in general is of course nonsense, because I can have C prime being a subpath of C, and then D being subpath of D prime. And of course, when they are not equal. Sorry, this was complete nonsense. But remember that CD is something which is longest in F7, F9. And the only way I can sorry, in F7 times F9, yeah. The only way I can get another loop which is also a longest is if I take a longest loop in F7 and the longest loop in F9, because if I take anything shorter, this will not be a longest loop in F7 concatenated with F9. All right. So I know that therefore I know that C prime is of the same length as C and D prime is of the same length as D. But then this holds if I have CD equals C prime D prime. If I can imagine that I can present my longest loop CD as another longest loop C prime D prime. Okay. That there is another presentation of CD. It's the longest loop, but it also appears in my sum under different incarnation. Now it's not C concatenated with D, but C prime concatenated with D prime. Let's assume it. But of course, if they are equal, they must be of the same length. They must be longest. And if they are longest, then both C prime, then all of them, C prime, D prime must be longest in the appropriate subsets. But this means that the length of C is the same as the length of C prime, and the length of D is the same as D prime. Therefore, this argument holds. Okay. Combining, we obtained a desired contradiction. Right, because well, I already know that my longest loop cannot cancel by anything from the first two summands, and now I'm wondering if in this sum, QQ prime, I can write it maybe as Q tilde Q prime tilde. Okay. But here, what is important that Q and Q prime, Q must be longest in F7 and Q tilde must be longest in F7. Q prime must be longest in F9 and Q prime tilde must be longest in F9. So this means that Q tilde is of the same length as Q and Q prime is of the same length as Q prime tilde. Okay, if I could present it in a different way in this sum, so that I can hope for some cancellation. But no, that's impossible because then I have Q equal to Q tilde and Q prime equal to Q prime tilde. So this particular longest path, there might be many other longest paths, but they are not the same as this one. So this longest path appears only once in that sum. And since it appears only once in that sum, It cannot be cancelled by anything in that sum. Remember the linear dependence. It cannot be cancelled by any element in the first two summands. So we must have a vanishing. This must vanish. And we get a contradiction because then this means that, remember, these coefficients are by assumption non-zero, okay? And so this contradicts the linear independence, okay? I have something which is not in the linear span of all other elements, and I have some non-zero coefficients times this equal to zero. So by the linear dependence, well, I have a contradiction because this coefficient should have been zero and it isn't. So this means that all in all, our assumption that F3 is non-empty was false. So we can conclude that it is empty. And when it is empty, we have the other inclusion. Span. Which ends the proof of a theorem. Okay, let me stop right now. If you have any questions, let's do them in the recitation class. So now we begin at 11:45, yeah, and we'll finish at the usual time, 1 p.m. So see you in a bit less than half an hour. I stop recording.